Let's begin our T-notes for oscillations. An oscillation is a periodic motion that repeats over time. There is a certain kind of oscillation called a simple harmonic motion, also known as isochronous oscillation. The definition is that it is a periodic motion where the restoring force and acceleration is proportional to the displacement and in the opposite direction of that displacement. The oscillation has the same amount of time for its back and forth motion. Its acceleration and velocity are constantly changing. A pendulum is an example of a simple harmonic motion. Here we have the string that is attached to a bob. The fixed point, also known as the equilibrium point, is located here in the center. And as the bob swings back and forth, you will have an increasing and decreasing of both the acceleration, the velocity, and the distance from the fixed point. Let me show you an example of simple harmonic motion. Here is a pendulum that has a pen attached, and the pendulum is swinging back and forth. If the paper on this conveyor belt is not moving, then we know that as the pendulum swings back and forth, you would just create a straight line. If the person begins to roll and spin this part right here so that the conveyor belt moves the paper and the pendulum is still swinging, you would create a wave, a sine curve. So you would actually create a motion that looks like this. Over here on the right-hand side, you'll see that there is a spring with a mass hanging on the end, and if it is pulled, it would allow the ball to move up and down, and if there is a pen attached to that, and again you'll see a roll of paper, if the roll of paper is moving, then what you would experience is again the drawing of a wave. There are certain conditions that must be true in order for an oscillation to be called a simple harmonic motion. Simple harmonic motion is also abbreviated as SHM for future reference. There must be a restoring force that is present, and this could be due to the gravitational potential energy as found with the pendulum swinging back and forth. It could also be in the tension that is from a spring that is being pulled either if it's hanging down from a ceiling or if it's being pushed back and forth on a frictionless plane. The third factor is that the magnitude of the force and acceleration is proportional to the displacement from the fixed point. So mathematically what that looks like is the relationship of acceleration and displacement is shown as the acceleration is equivalent to that of the displacement, and the negative sign just shows the acceleration is always in the opposite direction of the displacement. This is also true for force, and that is also proportional to that of the displacement. If we are discussing loaded springs, we would just need to put the constant, the K constant, in that situation. Notice the diagram below. Here we have a loaded spring that is on a frictionless plane, and it is moving back and forth, being stretched back and forth, and there is a fixed point, also known as the equilibrium point here. Notice that the force, which is shown in green here, and that the acceleration in red here is opposite the direction of the displacement. It is also the same magnitude as that of the displacement. For a loaded spring, this makes sense. As the spring is stretched further from the equilibrium point, the displacement increases, the tension increases, and because we know that F equals ma, an increase in force will therefore equal an increase in acceleration. You can use the displacement time graph to find the velocity at any given point. Likewise, you can find the acceleration at any given moment by finding the slope of a velocity time graph. Here are the two graphs that show if you were to find the gradient or the slope of a displacement time or a velocity time would give you either the velocity at that moment or the acceleration. When comparing the graphs for displacement versus time, velocity versus time, and acceleration versus time, you will probably be able to make out a few observations. Let's take a look at this displacement time graph here. And when x is 0, let's follow this line down, and what you will notice is that the velocity will be at its maximum and the acceleration will be at 0. Let's move along where the x is the furthest from the fixed point. In this case, velocity would now be at 0 and acceleration would be at its max, which is in magnitude. It's proportional to the magnitude of that of the displacement. From here, when the displacement is the furthest from the fixed point, let's bring it back. So now the displacement is again back at 0. So as it is returning, what we are noticing is that the velocity is increasing, and as it increases to its max, the acceleration would then be at 0. It's decreasing to 0. When looking at all three graphs together, you'll notice that they are sinusoidal graphs. They're sine curves. One thing you might not have noticed is that they start at different times, different points of the sine curve. We call this a phase difference. So there is a difference in time, or the stages, which one wave begins in comparison to that of the other graphs. So if we're taking a look at the displacement time, the velocity time, and the acceleration time graphs, they all start at different points along the sine curve. Let's take a look at the velocity time graph. And actually, before we even compare, let's take a look at what one full period is. And remember, a period is one full forward and backward motion. So in this case, we have from the lowest point to the lowest point. So if we were to part this up, this is 1, 2, 3, 4 parts. So you can think of this in quarters for one period. Let's compare the velocity time graph and when it starts. So here what we're noticing is that it is 1/4 a period later. So if we're taking into account that t is period, 1/4 of that would be t over 4, which is equivalent to 90 degrees, or pi over 2. If we're taking a look at the acceleration time graph here, and it starts right up here on the displacement graph, if you were to compare it, it has two portions, which is 1/4 each, and that is equivalent to lagging behind, having a phase difference of 1/2 the period of the displacement graph. So we have t divided by 2, also equivalent to 180 degrees, or in radians, pi. When taking into account simple harmonic motion, we do need to talk about how the energy is changing within the system. With the example of the pendulum that has no friction, there is a perfect exchange of kinetic energy to that of potential energy, specifically gravitational potential energy. When the bob is at the fixed point, in the equilibrium point, we have the velocity at its maximum. And so it is completely 100% all kinetic energy. As it begins to swing further away from the fixed point, there is a conversion between kinetic energy and potential energy until, of course, the bob gets to its maximum displacement from the fixed point. At that point, then what we have is all potential energy and no kinetic energy. As the velocity begins to increase and the bob returns back to its fixed point, then we have this switching, again, of the kinetic and potential energy, and it just swings back and forth between kinetic and potential energy. When you are graphing this, you will see that there is a direct correlation of this conversion. So when you have 100% kinetic energy, you have no potential energy. And likewise, when you have a high level of potential energy, you have the opposite amount of kinetic energy. So as kinetic energy increases, potential energy decreases, and vice versa. All right, so we are done with our TNOTES. Be ready to apply this information in class, and thanks for watching.